Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 7. Hello, who is it? Oh, there you are. Okay, how do dilations map segments? Opening exercise. Is a dilated segment still a segment? A segment's a portion of a line that has two endpoints. Dilate it, it's shorter and has two endpoints. Make it longer, it's dilated, it's got two endpoints. Yeah, of course. A segment dilates to a segment that is R times the length of the original. So now let's do that. B says dilate the segment PQ by a scale factor of 2 from center O. So what you do is you get your ruler and scroll to the top of the screen to get it. Okay. And put your ruler on, or 0 on O, like so. Draw a segment or a ray from O through Q. So that's ray. That there is ray OQ. Hello. What's going on with my pen? That is ray OQ. And then I put my ruler back at O. Rotate it so it's going through P. So this is ray OP. We're going to dilate the segment PQ by a scale factor of 2. 2 is more than 1. That means PQ is going to be, P prime Q prime is going to be longer than PQ. So let me put my ruler back where it was and measure. I prefer metric. So I start at 0 and I go to 3.123. So over here, I'm going to say OP equals 3.3 centimeters. Yours will be different on paper because this program dilates things. All right, so I take 3.3 times 2, so OP prime is going to be 3.3 times 2, which is 6.6 centimeters. So I'm going to put a dot at 6.5 plus 1 is 6.6 right there. I'm going to rotate my ruler down here, and let's make this a little bit better, and that will be P prime. So then I go back and I say, okay, well, OQ is how long? OQ is 4.5 centimeters. So 4.5 cm, so therefore OQ prime has to be twice that, or 9 centimeters. So I go and let's see, put a point at 9 cm, which is right here. Rotate my ruler out of the way, and there is Q prime. Move my ruler up to point P. Rotate it down to point Q. Let's get a little bit closer. And draw P prime, Q prime. So there is segment P prime, Q prime. So I dilated a segment by a factor of 2. It is still a segment. Okay, on to page 2. Part I says, is the dilated segment P prime Q prime a segment? Well, we've already answered that, and the answer is yes. The dilation of segment PQ produces a segment P prime Q prime. So as you can see, there it is. Whoop. Okay, so part 2 says, how, if at all, has the segment PQ been transformed? Well, PQ's here. It got moved away from our center of dilation, and it is twice as long. So we could say all of those things. So here's what we will say. Segment P prime Q prime is twice the length of segment PQ. The segment has increased in length according to the scale factor of dilation. Okay, and it's moved away from the center of dilation, but they did not say that. All right, moving on to example 1. It says case 1. Consider the case where the scale factor of dilation is R equals 1. Does the dilation from center O map segment PQ to segment P prime Q prime? Well, let's think. if the length of PQ, we never did measure those, did we? The length of PQ is 4.2 centimeters, or a little more, just moved. 4.3 centimeters. If I dilate that by a scale factor of 1, that means take 4.3 times 1, which is still 4.3. So P prime Q prime would just be a copy of PQ sitting right on top of PQ right in the same location. So how are we going to word that? It says a scale factor of R equals 1 means that the segment and its image are equal. The dilation does not enlarge or shrink the image of the figure. It remains unchanged. Therefore, when the scale factor of dilation is R equals 1, the dilation maps the segment to itself. Okay? All right, case 2, example 2. Consider the case where a line PQ contains the center of the dilation. Does a dilation from the center with a scale factor R not equal 1 map the segment PQ to a segment P prime Q prime? Explain. So let me draw the scenario to this. Let me draw a line segment. I'll make it blue, doesn't matter. Here's a line segment. I will label the ends PQ. Here's P. Here's Q. Does the dilation from the center with scale factor R not equal to 1? And the PQ contains the center of dilation. So if I put a dot on PQ and called that O, that is now my center of dilation. How would I draw my rays? Well, remember that when you do a dilation using rays, you start at the center and you draw a ray through the other point, and then you draw a ray through the other point, like so. So if OP were a length 1 and R was not equal to 1, say R equal 2, then P prime would be 2 times as long, or out 2 over here. So P prime would be right here. If OQ is 5, OQ prime would be way off my paper over here. Q prime would be way out here. So it would be a longer segment overlapping the original segment, but it would still be a segment. Okay, so that hopefully that made sense to you. So the answer to it in words is yes, the dilation sends point P and Q to points P prime, Q prime. Since the point P and Q are collinear with center O, then both P prime and Q prime are also collinear with center O. Remember, collinear means on the same line. The dilation also takes all of the points between P and Q, all of the points between P and Q, to all of the points between P prime and Q prime. Again, because their images must fall on the rays OP and OQ, therefore the dilation maps PQ onto P prime, Q prime, as in this picture. Okay. Page 3 brings us to example 3, and we have a case 3. Consider the case where line PQ. Okay, where is line PQ? Here is P, here's Q. So picture a line going forever through P and Q. Where line PQ does not contain the center O, center's over here, of the dilation, and the scale factor R of the dilation is not equal to 1. So therefore we're making it larger or smaller. Then we have a situation where the key point OP and OQ form a triangle OPQ. The scale factor not being equal to 1 means that we must consider scale factors such that R is between 0 and 1 and R is greater than 1. However, the proofs for each are similar, so we focus on the case where R is between 0 and 1. So we're going to dilate it smaller. And they show a diagram where OP prime, Q prime is smaller than OPQ. When we dilate point P and Q, Here's P, dilate it to P prime. Here's Q, dilate it back to Q prime. Okay, when we dilate them from center O by a scale factor of R less than 1 but greater than 0, as shown, what do we know about the points P prime and Q prime? All right, well, we know that P prime lies on ray OP. So P prime is on ray OP. And OP prime equals OP times the scale factor. And Q prime lies on OQ. And OQ times the scale factor. OQ prime equals R times OQ times the scale factor. So then we get a proportion where OP prime is to OP as OQ prime is to OQ, which equals our scale factor. The line segment P prime Q prime splits the sides of the triangle. It's a side splitter of triangle OPQ proportionally. Okay, by the triangle side splitter theorem, we know that the lines containing PQ and Q prime, P prime Q prime are therefore parallel. Okay, so that side splitter theorem is pretty cool. So now we use the fact that the line segment P prime Q prime splits the sides of OPQ triangle proportionally, and that the lines containing PQ and P prime Q prime are parallel to prove that a dilation maps segments to segments, because we already know what happens when point P and Q are dilated. Consider another point R that is on segment PQ. So they showed a new ray O going down here, and the point where it crosses PQ they call R is on segment P prime or PQ. So R here is on PQ. After dilating R from center O by the scale factor of R to get to the point R prime, does R prime lie on segment P prime Q prime? Okay, so here's the proof of this. So I just brought it all in and I will just talk about it. If you need to copy this, then pause the video and do so, but I'm just going to zip through it and read it. So it says, does R prime lie on the segment P prime Q prime if we did what this all said, drawing a ray through from O through P prime Q prime and PQ where R is on PQ, would R prime end up on P prime Q prime? Marlowe's proof of the statement says, let O be a point not on PQ, so there's O up there, and a dilation from O of some R scale factor be a dilation with center O and a scale factor between 0 and 1. That sends point P to P prime and Q to Q prime. So the let portion just sets up the diagram that we were given. If R is another point that lies on PQ, line PQ, then the dilation from O, scale factor R, of that point R is a point that lies on P prime Q prime. So the way we start this set is we say that the dilation D from O, scale factor R, with the center at O, scale factor R, sends points P to P prime and Q to Q prime, given. Since that is true, then we can then say that OP prime over OP equals OQ prime over OQ. So in other words, these two triangles are proportional. They equal the scale factor R, and that is by definition of dilation. Then we can say PQ is parallel to P prime Q prime by the triangle side splitter theorem. So now we know those two lines are parallel. Number 4, let R be a point on. Okay, my recording device failed, so let's start this again. 4, let R be a point on segment PQ. R is on PQ. Let R prime be the dilation of R by D, dilation, center O, scale factor R, given. Then we can say that OP prime over OP equals OR prime over OR, which equals R. That is definition of dilation. Okay, so now we go on to step 6. So now we have R prime here, R here. Now step 6 says, P prime R prime is parallel to PR. I'm sorry, PQ. Well, and PR because R is on PQ. And the reason is by the triangle side splitter theorem as applied to triangle OPR and the fact that the line PQ and PR are the same line. Okay, yeah. And then number 7 says line P prime R prime equals P prime Q prime. Okay, I can agree with that. I had to pause for a second. It's not a segment. So there is a line. So think of it as this. There is a line that exists right here, and that is line PQ. So line PR is equal to line PQ prime, PR prime. I'm sorry, I'm on the wrong line. Move it up to here. Hello. Okay. So what this is saying is P prime R prime is this red line. Well, it's also P prime Q prime because P, Q, and R are collinear. So we can say that the lines, since they go on forever and ever, it is the same line. So they are equal. So by the parallel postulate, through a given external point P prime, right here, there is at most one line parallel to the given line PQ. So I only have this red line that's parallel to PQ. There is the only line, it's that red one. The point R prime lies on P prime Q prime by step 7. So after all that is said in the proof, putting together the preliminary dilation theorem for our segments with the dilation theorem, we get dilation theorem for segments. So we just use another proof to create another theorem that we can put into our arsenal or our toolbox that we no longer have to explain. We can just say by the dilation theorem. So a dilation D about our point O of scale factor R maps the line segment PQ to a line segment P prime Q prime, sending the endpoints to the endpoints so that P prime Q prime equals R, the scale factor, times PQ. Whenever the center O does not lie in line PQ and R is not equal to 1, we can conclude that the line PQ will be parallel to P prime Q prime. Whenever the center O lies in the line PQ, or if R equals 1, then we can say that line PQ is equal to P prime Q prime. As an aside, okay, a side note, observe that a dilation maps parallel line segments to parallel line segments. Further, a dilation maps a directed line segment to a directed line segment that points in the same direction. A directed line segment array. Okay, anyhow. Page 4. Now look at the converse of the dilation theorem for segments. If segment PQ and segment RS are line segments of different lengths in the plane, then there is a dilation that maps one onto the other if and only if line PQ equals line RS or line PQ is parallel to RS. So either the same line or they're parallel. Okay, based on example 2 and 3, we already know that a dilation maps a segment PQ to another line segment, say segment RS, so that line PQ equals line RS. That was example 2. Or line PQ is parallel to line RS, which was example 3. If line PQ is parallel to line RS, then because PQ segment and segment RS are different lengths in the plane, they are bases of a trapezoid as shown. So what they're basically saying is if PQ and RS are not equal, like here, example 2, but in fact parallel, like example 3, and they are different lengths because they're dilated, then if you connect the endpoints of the segments, it creates a trapezoid. Since line PQ and segment PQ, and segment RS are segments of different lengths, then the non-base side of the trapezoid are not parallel, and the line containing them meet at a point O as shown. So you can do this with any trapezoid, and you could actually find a point where the sides, if were extended, would intersect, and that would be a point of dilation of one side onto the other, and the distance would be the common ratio or the scale factor. Interesting. So now it says, recall that we want to show that a dilation maps PQ to RS. Explain how to show it. All right, well, the triangle formed with vertex O, triangle OPQ, has PQ as its base. Makes sense? Since line PQ is parallel to line RS, then segment RS splits the sides of the triangle, side splitter, proportionally by the triangle side splitter theorem. Since we know the proportional side splitters of a triangle are the result of a dilation, then we know there is a dilation from center O by a scale factor of R that maps point P onto R and point Q onto S. Thus, a dilation maps segment PQ to segment RS. Okay, good enough? The case when segments PQ and RS are such that line PQ equals line RS is left as an exercise. Okay, page 5 brings us to that exercise, exercise 1. In the following exercises, you will consider the case where the segment and its dilated image belong to the same line. That is, when PQ, segment PQ, and segment RS are such that line PQ equals line RS, as in the diagram below. So here's the point P and R sharing this location. Q is here and S is here. 1. Consider points P, Q, R, and S on a line where P is equal to R as shown. Show there is a dilation that maps PQ, segment PQ, to segment RS. Okay, so in order to do that, here's what we would say. If we assume there is a dilation that maps segment PQ to RS with a scale factor so that R equals RS over PQ. So let me just color code this up. So what they're talking about is, here is PQ. Here is segment PS. Okay. So if we have segment PQ, and we're not PS, but RS, because P, it is PS, but it's also RS, with a scale factor so that the scale factor R equals the length of RS divided by the length of PQ, then the center of the dilation must coincide with the endpoint P and R, because by definition of a dilation, the center maps to itself. Okay, makes sense. So P is R. Since point P and R coincide, it must mean that the center O is such that O equals P equals R. So this is our point of dilation if a segment shares an end. Two segments share an end. Since the other endpoint Q of PQ, which is right here, lies on line PQ, the dilated image of Q must also lie on the line. So it's got to be on this same line. Draw the ray from the center through point Q, and the ray coincides with line PQ. Since the dilated image of Q must lie on the line, and point S is to the right of Q, then a dilation from center O with a scale factor r greater than 1 will map segment PQ to segment RS. So I just showed these above, but actually they'd be right on. So this is what the diagram would look like. Okay, number 2. Consider points P, Q, R, and S all on the same line. They're collinear. PQ does not equal RS. It's shorter. You can tell by looking at it. Show there is a dilation that maps PQ to RS. Where is the center of the dilation? Okay, so where's the center of dilation? Well, here's what we're going to do. We're going to construct perpendicular line segments of length PQ and RS through points P and R, respectively. So I'm going to get my compass and go to the top of the page and get it. I love that. Okay, here's my compass. Let's change the color to green. So construct perpendicular line segments with length PQ. So what I'm going to do first is put my compass stylus on P. Ooh, this is tough. All right, one moment. Okay, my pen failed, so I had to reboot that. All right, so anyway, we want to open this up and we want a radius PQ. Construct a perpendicular line segment of length PQ going through Q and of length RS going through R. So here is the length PQ measured with my compass. I put the compass point on Q and I draw a circle. Notice it's going through P. That is a circle with the radius PQ. So the distance from Q over to P will be the same as the distance from here up to here. If I do a perpendicular line of intersection now, don't want to move the background. Oh, come on. Okay, so if I want a perpendicular line going through a segment, how would I do that? First thing I want to do is, okay, so I'm going to open the compass up just a smidgen more. Let me change the color to blue. So I'm going to make this a little bit open further, and I'm going to use the point P to draw an arc over here, and then move my stylus to the other point of intersection of that circle I created, centered at Q, and draw another arc there. And where those two intersect is where I would take my ruler, which is at the top of the page, and bring it down and rotate it. And that arc and that segment should be a perpendicular. Okay, so let me just erase that. I don't want it going beyond Q. So there is a segment. And then if I shorten it to here, let me erase that. I should have only gone to the circle. There is a segment of length PQ perpendicular to the line. Then I repeat that process again. Bring my compass up here, straighten it out, put it right on R, best I can, right at the center. Much easier on paper than it is on computer. Okay, pen went crazy on me again. All right, so there's that. One moment. Okay, so now I'm going to make a circle there. Let's change the color because I've already used blue. Let's make it purple. There is the circle around our length, radius RS. And then I'm going to bring my compass. Actually, I should have left it. No, I have to bring it over here. Put it at this intersection. Open it wider than that halfway and draw an arc. Bring it over to here on S. Rotate it around and draw an arc. Where they intersect, that is going to be my vertical or my perpendicular line to R through R. So now when I draw this, I'll use blue again. And I only want to go up to my circle. Okay, so there we have it. So I've constructed perpendicular line segments, length PQ through point P and R respectively. Okay, I did it through Q. Whoops. All right, so just to save time, I'm going to move that over and center this here. My apologies for that, but at least you saw the process. And then I will move my vertical line over here, and it's going through P, length PQ. So I apologize for that. I should have centered that circle at P, not Q, and these two marks over here should be over here. Anyway, there's the two segments, perpendicular to P and perpendicular to R. So note that the endpoints of the perpendicular segment, Q prime and S prime. Okay, so we're going to name the endpoint here Q prime and name the end of R up here S prime. Draw an auxiliary line through points Q prime and S prime. So then I bring my ruler over here and line this up. Like so, and here's my auxiliary line. Okay, going through Q prime and S prime. That intersects with line PQ, which is down here, and there's the intersection. The intersection of the two lines is the center of dilation O, so I will label this O. Since line PQ prime is parallel to line RS prime. I just did segments, by the way. That should not have arrows here and here. Okay. Since PQ is parallel to RS, perpendicular lines by the triangle side splitter theorem, the segment P, Q prime, splits the triangle OR or RS prime proportionally. So the dilation theorem, the length of R S prime divided by P Q prime equals R dilation R. This ratio implies that R S prime equals R times PQ prime. By construction, PQ prime equals PQ. So PQ prime equals PQ because we constructed it using these circles. And RS prime equals RS. Therefore, RS equals PQ. RS equals R times PQ by definition of dilation. And since RS equals R times PQ, okay, there's a dilation from center O with a scale factor of R that maps PQ to RS. So this just proved that PQ is a scale factor of RS or vice versa. And the scale The center of dilation is O. Okay, that was kind of a neat way to look at this. And that is the end of this page. Okay, page 6 brings us to the end of lesson 7. Review the lesson summary and go do your problem set.